All right. I guess we can start the last talk of ECC. And so we're going to listen to Agustín Domínguez-Oviedo from Querétaro. And he's going to talk about fault-based attacks and countermeasures for elliptic curve cryptosystems.
Thank you for the introduction. Let's start. I will give first an introduction to the topic, some background stuff that we need to understand better these concepts. Then I will describe invalid curve attack on Montgomery's ladder algorithm. And then I will talk about error detection strategies that we can take, we can have. And in 5 and 6, we will have, in 5, we will have solutions that are inside the scalar multiplication. Like we in a high level design, we will add protections to faults there. And then in number 6, we will go in algorithm level, in this case, solutions for preventing these attacks. And finally, some conclusions. First, security of cryptosystems relies on mathematical problems that are believed to be intractable. However, in practice, cryptosystems are implemented using some kind of programming language or maybe hardware circuits which run in some sort of computer. A computer is computing these algorithms. In real life, an adversary has a lot of possibilities to break a probable secure cryptosystem, even when theoretically it seems that that cryptosystem will be secure. The implementation can help us to break a system. Cryptanalytic attacks may reveal some system vulnerabilities, which then need to be fixed with countermeasures. Actually, fault attacks were introduced by Bonnet, DeMille, and Lipton, and those attacks take advantage that errors that occur while computing a cryptographic device is performing a private key operation. Then, if we can induce a fault and we give the result, the attacker can retrieve some part of the key or maybe the complete key. Then it's important not to leave the result if we find some errors. That's very important, error detection during any cryptographic computation. Fault-based attacks were introduced by for ECC were introduced by BL, Meyer, and Mueller in 2000, and actually these authors have two in this case attacks. One is invalid curve attack, and the other one is an extension of other previous attacks, and is called differential fault analysis attack. Basically, for this attack, the attacker just make a fault in some part of the algorithm, and then if the final result is released, they can use that faulty result in order to retrieve the key. An interesting paper was for this other attack is for these authors, Blumer, Otto, and Schiffer, and they proposed the sign change fault attack. Basically, this attack is based on attacking an intermediate point during the scalar multiplication. If we can inject a fault in a sense that at y coordinate we can change the sign of this y coordinate, then we change the sign of that point, and if we could do that, it's possible to retrieve the key. And an interesting thing of this attack is that the point verification does not help to prevent this attack. Let me explain you this principle. Basically, here we have the left to right scalar multiplication algorithm by double and half. And here, if the attacker can inject a fault in this queue in the iteration I, then the faulty result before the fault is a normal operation, and then after the fault we have this change of the sign of this point. Then with this equation we can see that if I is small enough, we can retrieve the I plus 1 least significant bits by exhaustive search. And That's why this, an interesting thing of this attack is that the result is part of the original elliptic curve, doesn't leave the original elliptic curve. Then the point verification is not enough in this case. For example, we can always, in all the scalar multiplication algorithms, at the end is recommended to verify if the output point is part of not of the original elliptic curve. If it's not, we shouldn't give any result. But for this case, for the sign change attack, this countermeasure is not enough. We need to add something else. Those authors put these countermeasures, and basically they use first we have a point that is in the original elliptic curve, and then they select a smaller prime number called R, and then they obtain a combined curve. Then this combined curve is in a ring PR, where P is the prime that is used for the field, or for the prime field, and R is this prime that is selected here. Then we have we need to perform two scalar multiplications, one in the combined curve and the other one in a small curve. This small curve, the computation is not most costly because the R is small, but this one, yes. Then you release the result if you find that those points are equal mod R. Here we have a problem, like this is a countermeasure to this attack. However, first, this algorithm can be only used for projective coordinates. Why? Because step 3 is in a ring. In that ring is prohibited to have inverse multiplicative. We cannot have the inverse multiplicative. Then the author says that this algorithm must be implemented in projective coordinates. Then also, this line 3 increases the moduli that is performed the operation. For example, for these parameters, T192 and R are 80-bit numbers, the modulus is increased by more than 40%. That tells that this operation is much more costly than the original one. I will talk about attack that we proposed last year, basically in a paper. I will mention the papers after the presentation, but tells the necessity to detect errors, and more if one algorithm that is very popular is used, such as Montgomery ladder algorithm. Basically, the idea is here we can have points in this elliptic curve. And then if we have in this elliptic curve that is defined over the binary field, if we have this curve, those invalid curve attacks proposed by Biel and in other paper by Sieta and Joyce are based on the property that in group formulas, in some group formulas don't use parameter B. If parameter B is not used, then you can mount this invalid curve attack. However, this is not the case for Montgomery's ladder. Montgomery ladder, proposed by Lopez and Dahab, that is a very popular algorithm. Parameter B is considered for point doubling, but parameter A is not used. Okay? Then we can exploit this. This is Montgomery's ladder algorithm proposed by Lopez and Dahab. Basically, here we have two intermediate points, and we only use the x-coordinate. We compute only obtain the x-coordinate of these two points, and at the final we obtain the y-coordinate of the result. Okay? The function for the point adding with this small x, this function, is basically like this is the group formulas. Here, if it's point doubling, we use parameter B. And if it's point addition normally, we use this formula. And we can see here that parameter A is not used. Okay? Going to some theoretical things here, we can have, if we define two non-supersingular elliptic curves over the binary fields E and E bar in this form, we know that are isomorphic over the binary field if and only if the trace of the parameter A is equal and the parameter B is equal also. If this is true, these two curves are isomorphic. Actually, for a fixed parameter B, there are only two isomorphic classes of curves. One that the trace of A is equal to 0, and the other one that the trace of A is equal to 1. Let me define two elliptic curves with this of each of these isomorphic classes. In this case, we have the class with A equal to 0, and in this case, A equal to 1. If we define these two elliptic curves, we can find properties like, you can see here why I want these curves. Because one curve will be the one that is recommended by NIST, and the other one, hopefully, could help us in order to mount an attack. Okay? Then we found some properties of these two curves. Basically, these two curves only share 2 points. The point at infinity and this point of order 2 that is 0 square root of b. They are the only points that they share. Also, we can see that if we have a point in one curve with its x coordinate, there are not any other point in the other curve with the same x coordinate. Okay? I will give an example that we will clarify this. Also, all the final field elements are covered for x coordinates. Like we have in the x coordinates, we have that either one curve or the other will contain a point with a x value equal will cover all the final field. We will see this in the example. And if these three are true, then we have this relationship between the orders of one curve and the other. Let me explain you this. For example, here we have this small curve in the binary field 2 to the 5, and we can see here that these two curves only differ in parameter A. Here A is equal to 1, and here A is equal to 0. Basically, we can see here that the 2 points that they share is the first point and the last point. 0 and 1, and here we have 0 and infinity. The rest of the points are different, and we can see that all the values of x coordinates of the final field are covered. For example, here we have 1, 2, 3, 4, 5, 6, 5 here, and 6 is in the other. 7, 8 is in here, 9, and so on. And we cover all the rest of the points. That's important for our attack. What happened? This was a small toy example, but what happened with NIST recommended curves? For those that are the binary randomly curves and all the curves called Koblitz curves. Here we can see this is the standard one, and with parameter A equal to 1. If we have a parameter A equal to 0, we can see here that it's a weaker curve. The order, we have this factorization that is below. It's weaker, of course, than the standard curve. For 233, we have similar case where the weaker curve with the only difference between these two curves is the parameter A, right? It happens for from the 10 cases of the NIST recommended curves, it happens that we have a weaker curve in 9 of these 10. We can here, I will pass quickly these curves, but basically we can see here that the other curve is weaker. This is the only exception that is not. Koblitz in 283, the one curve has this order, and the other curve is also an almost prime number. This is the only exception, but the rest of the couplets, that's the case that we have a weaker curve, only changing the parameter A. Okay? We can see here the size of each prime factor of the order of the group for each cases, for the 10 curves. And we can see here that we have, in 9 of the 10 cases, we have the least recommended curve and a weaker curve. The only exception is 283, when we have, there's no weaker curve there. From under the attack, what is the idea? To perform the computation in the other curve with different parameter A, and because Montgomery algorithm doesn't take in account A, and if we reveal the result, we can obtain the secret. We consider that we have a cryptosystem using a strong elliptic curve, for example, those recommended by NIST, with parameters AS and BS. And we assume that there exists a weaker curve with the same parameter B, but with different parameter A. Okay? This happens for 9 of 10 NIST recommended curves. What is the idea? Basically, we can we have this computation, we have the input point, and if we can inject a fault in the x coordinate of the input point, we can obtain P tilde. P tilde is not longer part of the original elliptic curve. Actually, it's not part of an elliptic curve. Even it's not part of the other curve, because Py has another number. However, if we know this P tilde and we give the result, we can retrieve the scalar in this example. I will show you how. Basically, if we inject a fault and we obtain P tilde, and it's easy to verify if there exists a point in the weaker curve, in the weaker curve that has the same x coordinate as my faulty input. If I randomly choose a bit in the x coordinate, there's approximately 50% chance that I got another point in another curve, because for a big field, half of the points basically are in one curve, and half of the other are in the other curve. I mean, half of the values of x. Okay? Then, if we obtain this q tilde, we can obtain q hat, that is a point on the weaker curve. Similarly here, from P tilde, we can have P hat, that is a point in the weaker curve. If we have these two, then using the Silver-Pauling-Hellman's algorithm, we can obtain, in this case, K mod n, and the attacker with only one pair of faulty of P hat and Q hat, the faulty point and then the result, and with some acceptable amount of excessive search, we can retrieve the full scalar. Basically, for example here, permitting with E equal to 10, E is a parameter that is used for telling us how much of exhaustive search we can compute. In this case would be 2 to the 10, that is nothing, right? If that's the case, the probability of having a random point, like a random fault, we put a random fault, and that random fault gives the full scalar, is very close to the unity. What about the countermeasures to this attack? Basically, one can use formulas with both parameters A and B. The problem is that more computations are required, and for performance degradation, we don't want performance degradation in this case. The other one will be to select a correct curve. In this case, we can use, for example, the NIST couplets 283, but this is too restrictive because we have 10, and these curves are good if we take care about the implementations. And how can we do that? For example, point verification. Point verification, we can check if the input point is part of the original elliptic curve. This will prevent to change the value of P. And then, if we could bypass that input verification, then it's very important to have also point verification at the output to verify that the output is part of the original elliptic curve. Okay? Not as the previous examples where the point was revealed to the user. Right? Another could be used coherency check. I will explain this later. But basically, in this case in ECC, we need to have error detection, and point verification is not always enough. The sign change attack is one example of this one. Then, for error detection is very important from the security point of view, and also if we have a very good error detection scheme, it's possible to have even some fault-tolerant schemes. Some fault-tolerant schemes that are working, and even if you have faults or that can be even naturally, these faults, the system could give you the correct result even if you have some faults. This is fault tolerance design, and in that concept we need also to have very good error detection schemes. The first strategy that we use is a simple one, is point verification. Point verification of the output is very important, sometimes in the input as the previous attack that I presented. Okay? Another countermeasure, but here in point verification we saw that the sign change attack is not enough for that attack. For this attack is not enough the point verification. Okay? Then another approach will be using some modular design that is called repeated and parallel computations. For example, here we can compute the same scalar multiplication twice, but differently. Like we'll compute the same scalar multiplication, but using some encoder and decoder, we can detect errors that happens here. Even if you have a permanent error or the same error in the same place, you will detect that one because you have an encoder and decoder. Obviously, this scheme, the problem is the performance because you double the running time. But you can also have parallel computations when you compute the same operation twice, but one with the encoder and decoder process. In order to detect errors, even if the errors are in the same place, you will detect those because you have this encoding and decoding process. Another approach for error detection could be using coherency or consistency check. What is that? Some operations can give us, at the end of the algorithm, some pattern, and this pattern could be useful for detecting errors. We will use that as well. First, for a high-level solution, we have these assumptions. We are working in a high-level design where the elliptic curve scalar multiplication module is the main block. Okay? This block can be implemented in hardware and may become faulty because natural causes. There are many causes that can be like a radiation or maybe some noise or X-rays that can be, as a product of that one, we can have a faulty model, or can be faulty because we have an attacker there. We consider that other modules are less complex and are implemented in a secure environment or even in software or hardware. Okay? And also we consider that the input and output are in projective coordinates. If we have that, we can use this encoding process for the input point. We can use one randomized version of the original point. How to do that? For example, in Lopez-Zahab projective coordinates, we can only do these operations and we obtain a randomized version of this point. We can use that one, that concept. We also can use, for encoding the scalar, we can use a scalar, but we can add the order of the group, a multiple of the order of the group. If we do that, the scalar multiplication will be the same, but we will use every time we will use another different representation of the scalar. This could help us also to have a good encoding process. If we would do that, for example, here we can have a recomputation scheme when we recompute the same operation twice, but using different encodings. If we do that, we can prevent, for example, the sign change attack. Why? Because sign change attack, for example, randomize the scalar. If you randomize the scalar, then the attacker cannot know. Basically, it's useless for the procedure of we have this sign change attack. Okay, but the problem here is that the running time, it doubles, right? Then we can have parallel computation that we perform we have two modules in parallel, and we do the same point encoding and scalar encoding using this randomization of point and scalar. If we want to have a fault-tolerant scheme, the first thing that we can have in mind is the well-known triple modular redundancy. What is that? You can repeat the same operation 3 times, and then with a major volter, you can decide which one has the correct result. Like if the 3 modules are running normally, basically the 3 outputs will be the same. That's no problem. But what happens if one of them is faulty? If one of them is faulty, then the other 2, because it's a majority voter, can decide which one will have the correct result. Here is clearly that the problem with this scheme, you have a fault tolerance, because you can have faults combined that are inside one of these 3 modules. However, the problem is that you have 3. In this scheme, for example, we can have a fault tolerance, but we have only 2. Why? Because point verification or point validation can tell us which one is fine. If we do that, we have only 2 modules using this point encoding and scalar encoding, and point verification will tell us which one has a correct answer, or if both are faulty, we can see that in this model, the point verification, if both give us incorrect results, then we are not giving any result, because both point verification process tell us that both results are incorrect. Those are solutions at high level. But what about if we go inside the algorithm? For example, here we can add solutions to inside the algorithms. One protection that we can add is point verification, of course. The other one will be specific functions for coherency check, to check this coherence between variables in the algorithm. We assume that any variable that is used in the elliptic curve scalar multiplication algorithm can be target of faults. Then you have one input, one variable, and then after a fault it becomes something else. For Montgomery ladder algorithm, we can use 2 approaches. One is the well-known point verification. We have the Montgomery ladder algorithm only computes the x coordinate of the intermediate points Q0 and Q1, and also we have the input point which coordinates are x and y. In the final part of the algorithm, they use a function j. In that function, in that function, it computes the y coordinate of the result. After that we compute point verification, we can detect some errors. Okay? Another approach could be using coherency check. Why? We can use coherency check here because the Montgomery's algorithm assumes that the difference between these 2 points, Q0 and Q1, is p. The difference in each moment of the algorithm. And if this is true, then at the end you can perform a point addition with p, and then you need to obtain Q1x, the x coordinates of Q1. We studied these two approaches, and we found that both approaches are equivalent in terms of error detection, if and only if the input point is P, or in other words, that the integrity, we are sure that P that is used and the final of the algorithm is the same input point. For that, we can do an integrity check only. Okay, and what about to have another approach for resisting this sign change attack? We investigate what could be useful, and we were looking for algorithms that have a strong coherence between the internal variables. Okay, and we found this one, the double and not always algorithms. Those algorithms, basically, we have two versions. One is left to right, and the other right to left. But basically, we found that the right to left can, in this case, can resist the sign change attack. Let me explain both of those algorithms. This is the version of the left to right double and not always. In each step, we have a point doubling, and we have a point addition as well, because that's why it's called add double and not always. But depending on the value of the bit, the scan of the scalar, basically you update either Q0 or Q1 here. If we use this algorithm at the final of the loop, we have that Q0 is the result, but Q1 has another scalar multiplication that is the Hamming weight of the 1's complement of K times P. Then we can use this coherency check function in order at the end to check if our internal Q1, the final result, is equal to the Hamming weight of the complements 1 of K, P. If not, we will not release the result. Function C3 detects any alterations that we have in Q1. We can see here. Q1 is used here, but Q1 is, the one that is independent here of this operation is Q0. But Q1 is updated only here, and then we can detect any alteration in that variable. However, the attacker can mount a sign change attack in this algorithm if the sign change target is this point, Q0. This is not resistant. This left to right algorithm is not resistant to sign change attack. However, if we use the other version, the right to left double and add always, what happened here? We scan the scalar from the least significant bit to the most significant bit. If we do that and we use this algorithm, Q2 is the one that will keep the point doubling for each loop. And Q0 and Q1 will have something depending on the scalar. If we look the relation between these three variables, even could be in the final, but could be even in the middle of the algorithm, we can notice that if we add Q0, Q1, and P, we will obtain Q2. And this is always an algorithm, and more in the final is of our interest. Why? Because we can define a coherency check function 4 that checks that this final result of Q2 is equal to the point addition of Q0, Q1, and P. If we do that, we will resist the sign change attack. How? I will have some examples here, but basically, for example, here we have error-free computations with a scalar equal to 909. We have the 1's complement of the scalar, and is this 114. And we can see here the values of the variables without any error. And basically here, we can see at the final that if we add these two plus P, we obtain this one. And actually, this can be done in any part of in any iteration, not necessarily at the final. Okay, but what happens if the attacker mount an attack in a sign change attack in Q0 in this first point at the iteration I equal to 4. From I equal to 4 and here we will have this point will be infected. Actually, that color is red, believe me. But what happened here, that if we add these 2 points together, we won't obtain Q2. Okay, and that's for an attack in Q0. What happened in the other point, in Q2, if we mount a sign change attack, here the coherency will be infect the 3 points. Why? Because Q2 is used by these two Q0 and Q1, depending on the bit, the scalar bit. And after the final result, we will see that the coherency doesn't match, and then we detect that error. In that case, this sign change fault attack. Which countermeasures are known for this fault sign change attack? First, if we use affine coordinates, one countermeasure, natural countermeasures, could be using Montgomery ladder without y coordinates. Why? Because if you don't use y coordinates, you cannot change the sign, right? Because the sign, you need to do a flip in the sign of that y coordinate. But you can also, the authors of sign change attack talk about that this algorithm has some patent issues, and it's not, you need to pay like in order to use. That's why they propose this combined curve solution. However, algorithm 5 can be used in affine coordinates also. In projective coordinates, we can have the Montgomery ladder without the y coordinates, of course. The solution that the authors gives using the combined curve. We can use the schemes that I presented before, the recomputation or parallel computation, with the problem of this doing the same operation twice or in parallel. Or we can use algorithm 5 as well. What happened with the overhead of this algorithm 5? If we use in terms of the final feed operations with t equal to 192, actually for affine we don't have much overhead, and for projective we have 28% that we calculate. And why we have this big change between projective and affine? Because here this 28% assumes that the algorithm, if we use the right to left version, we cannot use mixed coordinates. If you don't use mixed coordinates, the group formulas that we need to use are more costly in terms of final feed computations. That's why this algorithm, this right to left version in projective costs more than 28%. Here we have talked about an invalid curve attack on Montgomery's ladder algorithm, and actually that algorithm is over the binary field. We have talked also about error detection and fault tolerance in the elliptic curve scalar multiplication operation using repeated and parallel computations, and this even can help us to resist known attacks. And even we can have fault tolerance. That's an advantage to have a fault tolerance system is that even if one of the models are faulty, you can still give a result, because sometimes faults comes in natural causes. Okay, and then we have seen algorithm level error detection in this scalar multiplication, and we have used the concepts of point verification, coherency check, and integrity check. For more information about this, I tried to summarize these 3 papers in this presentation, but if you are interested in some more details, you can find in these 3 articles. Muchas gracias.
So we have lots of time for questions.
Thanks for a nice presentation. I have a couple of questions. The first one is regarding the sign change attack. Can you elaborate a bit more? How do you change the sign of a point, for example, in hardware design or in software design?
Yeah, actually, those authors call, for example, if you have an ALU that is performing these point operations, usually those units have a bit that depending of that bit is 0 or 1, you can use the normal point or the normal value of the value with this two's complement, basically. That's what says the authors. Like in some, for example, in some crypto processors, if you are implementing these print fields, normally you can. Sometimes you need to do a point rest, right? To obtain the, depending of the algorithms, will be like to obtain the negative point. And if you have a bit to select, if you want the normal point of the point, the inverted point, then you can target in that particular place. It's a very sophisticated attack because you need to know details about the hardware implementation, but the author says that it's possible.
Yeah, I think it's very specific in a way. It really depends on how you implement it. I think many designs don't really use one bit to use a point Q or minus Q.
Yeah.
Okay, so anyway, that's a paper from other authors, right?
Yeah, that's right.
So my second question is related to the majority voting. So you have like parallel implementations of the algorithm, and then in the end you use a majority voting. But suppose you're using, the attacker is using, for example, a glitch on the clock or a glitch on the voltage. In that case, then the fault will be exactly the same on all the computation modules. But then in that case, the majority vote will not work, right?
No, yes, because you are using encoding and decoding process. If you don't use encoding and decoding process, that's true. Actually here, if you are using encoding and decoding process, even if you have the same fault in these three models, the result will be different.
Okay, so basically you cannot have the same fault on three modules.
Yeah, but if you you say that if you target the input voltage, and this voltage is for all these three models, yeah. Even if you, in the worst case that you have the same fault, you will detect those faults. Okay. Because you are using this encoding and decoding. If you don't use this one, if you can inject a very precise form in each model the same fault, then you are not going to detect those errors, and you will give an incorrect result. Okay.
My third question is regarding to the
we have time.
Yeah. So I almost forgot what was the third question. So I think was the dub and add always. In the end, you added one point validation. So we know that dub and add always algorithm has dummy operations there. Yeah. The dummy operations open the window for fault analysis. Yeah. So I assume that in your algorithm, this dummy operation is kind of removed, or there's no dummy operations anymore.
Yeah, you have dummy operations because depending on the scan value, you will update one variable or the other. But the thing here that the coherency check, actually for example here, for example in this first version, the left to right algorithm, if the dummy operation could be here, but it's the only part that the dummy operation can be used, because this operation will update either Q0 or Q1. But in terms of our currency check, it will check if Q1 has any alteration. And that's why this will resist the safe error attack that you call. And more than this one, if you have any error in the computation, like those that are used for safe error attack, with this currency check, you will also detect those errors.
No, I mean the left to the right version of DABA not always. So you say that
the left to right?
Left to right. So you say that there is dummy operation. So that's 2.2 or?
Yeah.
So basically KI can be overwritten because of?
It's not really a dummy operation because here you will update, the point addition is always used.
Okay.
Okay?
Yeah.
But you will update either Q0 or Q1.
Okay.
Okay? Because you have here this QI bar.
So no point is getting overwritten basically. No point is really ditched during the computation.
Yeah, during the computation all points are used.
Okay.
However, in this case we can have a same change attack in this Q0. No safe or error because you don't have you have like you don't have dummy instructions because you will always here update one of either Q0 or Q1.
Okay. So in
that's a modified version of the original double and add always, because the very original double and add always have a dummy instruction that is not used. Yeah. And then the attacker, if can mount a fault there, either if you give the result or not, will tell the attacker this is scan bit of the scalar.
Yeah, yeah. Okay. Thank you.
You're welcome.
Sorry.
Yeah, that's right.
What was the question for the rest of the room?
Yeah, actually, yeah, there's one error here because Q0 must be initialized with P. I think, yeah, we have here Q2 equal to P. Yeah, that's right. Good observation.
Other questions? Oh.
I have one question. It seems to me that all the methods that you have presented here, Agustín, apply also for prime field elliptic curves, but is that correct?
Not all, because, for example, the attack is only for binary fields, Montgomery ladders in the binary field, because we have these isomorphic classes that if we fix a parameter B, we have only two different curves. Right. Okay, in that one, it cannot be extended for prime field, but for the rest of the algorithms, for example, is for the case in algorithm level protections, we can have both. Mm-hmm. That's why here I use this for binary field. For binary field, this is representation, but could be for prime fields as well. Actually, for prime field is of interest if you can mount a sign change attack, because in binary field it's not possible, because in binary field to change the signs of one input point you need to do a final field addition, and it's much more difficult than change a sign of one coordinate.
So you were mostly interested in binary field elliptic curves. That's why most of the examples are in.
Yeah, okay. That's right. But this can be applied also to prime fields, and actually is of interest to be on prime fields, because in prime fields we can resist this sign change attack. This, for example, this slide is referring only to prime fields, because in prime fields we can have this sign change attack, in the binary field not.
Other questions? I have one. So you just said to Yongfeng that if you actually want to perform an attack, you need some very sophisticated tools or maybe money. So imagine I have all the equipment, all the money to flip one bit on the circuit at a very precise time. So I need to know to do that. I need to know exactly the structure of, I need to know the algorithm, I need to know the architecture, I need to know everything about the circuit, including all the countermeasures that you've implemented. Don't you think that such a powerful attacker can also flip whatever bits is needed to counteract your own countermeasures?
Yeah, of course. Like that's why we call that the only model that can be faulty for the modular design could be the scalar multiplication algorithm, because if you can inject a fault in the point verification or in other models, there's no way. But usually the more complex model is that one. To the point verification or other like the comparator, voter, or all those models are much less complex, and then you can use other techniques to detect errors in those small models. This is overhead.
So I guess it's all for questions. So thanks the speaker again.
Thank you very much.